Hello and welcome to week 3, lecture 2 of CO 442-642 graph theory. Today we'll be doing a proof of Vizing's theorem. To remind you where we left off from last lecture, we had introduced Vizing's theorem, proved in 1964, which says that if G is a graph, then the chromatic index, denoted chi prime of G, is at most delta of G, that's the maximum degree, plus 1. And I will have to remind you further of some key definitions and concepts we saw in last lecture, which we used in an alternative proof of Koenig's theorem. One was Kemp chains, introduced by Kemp in the 1800s. So a Kemp chain, I'll give you a partial k-edge coloring of a graph G, call it V. If A and B are colors in K, 1 up to K of course, and a vertex V of G, then the AB chain at V and Phi, denoted with the somewhat strange notation PV, AB, Phi, is the maximal path cycle of A and B colored edges containing V. So we saw how to use Kemp chains last time. An important idea was that of switching. So the coloring phi prime obtained from phi by switching, also known as recoloring, is defined as, well, basically you switch A and B on the path PV, AB, Phi. So that was switching, and lastly was this concept of missing colors. So somehow it's more important what colors are missing around vertices than those that are present. And so we say a color A is missing the vertex V if it doesn't appear on any edge incident with V in this coloring phi. And in a terrible abuse of notation, we let phi of V denote the set of colors that are missing at V. So we used these ideas last time to give an alternative proof of Koenig's theorem, very nice, and that's what we'll do today. We'll use these concepts to prove Vizing's theorem. Now, what we're going to be doing is giving an alternative, slightly alternative proof to the proof that appears in Diestel. And in particular, though, we'll introduce a definition. So here he has a concept that he uses in the proof, but he doesn't really give it a name, but here we'll give it its standard name called the Vizing fan. So here, what is a Vizing fan? Suppose that G is a graph, and I'll give you an edge E, and I'll do a picture in a second. V0, V1 in G, and I give you a partial coloring phi, and it's going to be a k-edge coloring for some integer k, of G minus E. So imagine we're trying to prove Vizing's by some induction. We delete E, we get a coloring of G minus E, and now we want to extend it. So Vizing fans will help us to understand when we maybe can't do this. So what is a Vizing fan? Well, we say T is a Vizing fan with respect to the edge E, the vertex V0, and the coloring phi if these are all disjoint. And for every j from 1 to n, ej is equal to vj v0, so that would mean it's a star with center v0. And for all j from 2 to n, the color of the edge ej is missing at one of the earlier vertices from 0 up to j minus 1, so some I. So that's a Vizing fan, and here's a depiction of the Vizing fan. So v0, v1 is our edge E, and that will be uncolored, again in this partial coloring. And now what? Well, so we're going to have a star with center v0, so v0, v2, v0, v3 as edges up to v0, vn. And then we're going to have colors on the other edges that aren't v0, v1. So actually, if you think about it, because it's a proper edge coloring, then all these colors are distinct. So you have alpha 1, alpha 2, up to alpha n minus 1. And each one has to be missing at some earlier vertex. So for alpha 1, well, all these colors and all these alphas appear at V0, so then for alpha 1, it only has one choice, it has to be missing at V1. And then alpha 2, well, I've drawn it here like it's missing at V2, but of course, if V1 had actually smaller degree, if it wasn't a regular graph, then indeed it could be missing at V1. So this is only a depiction of a possible case. If you want to assume the graph is regular by embedding it in a regular graph, which you could, then it would be more forced as in the picture, but this is just a depiction. So a Vizing fan, we have a star, we have one edge missing on that star, V0, V1, and then again the edges of the colors of the other edges of the fan are missing at earlier vertices, somewhat as depicted. So that's a Vizing fan. What are we going to do with it? Well, we're going to prove a key lemma, a very nice lemma, and it goes like this. The idea is that if there's no coloring, so if we have this coloring and we can't get a new coloring that extends to E by switching on Kemp chains, then it turns out there'll be disjoint missing colors for the vertices of the Vizing fan. Or a bit more formally, we would go like this. So let G be a graph and E, V0, V1 be an edge, And suppose for some integer k in here, I'm going to assume that k is at least delta of g plus 1 for reasons to make the proof work. And so suppose we have that, and we have that g minus e has a k edge coloring, but g does not. So that was the situation. We're trying to kind of inductively, we'll apply this to get a rather short finish to the proof of Vizing's when we're trying to do induction or kind of minimum counterexamples. So we have a k edge coloring of g minus e, but not of g. And if we let phi be such a k edge coloring of g minus e, and t be a Vizing fan with respect to e, v naught, and phi, so here as we've set up, we've had a coloring, and then we get a fan based on it, then the claim is that the missing color sets are disjoint. So phi of vi is intersect phi of vj is the empty set. So they are actually disjoint for all distinct vi, vj, and v of t. So here's this amazing lemma that these missing color sets, if you can't get a coloring, they are actually all disjoint. And we're going to use that fact to give a proof at the end of Vizing's that'll be relatively straightforward. But here now we'll proceed with giving the proof of this lemma, this key lemma. So how does the proof of the lemma go? Well, suppose not. So we'll go by contradiction. What would that mean? That means there is an I less than j in 0 up to n, right? There'd have to be some I in j where phi vi intersect phi vj is non-empty. And here I'll assume I is smaller than j just for convenience. And then what I do is actually let's back up and choose phi t, I, and j be chosen such that j is minimized first of all, and subject to that condition I is minimized. So here's the real key, is we're going to choose cleverly the phi t among all the possible options, the I, the j, so to minimize j, that larger term first, and then subject to that to minimize I. So that will smooth our proof and give us some notion of progress as we do these contained switches. Okay, so then what? Well, we're going to let alpha be in phi of vi intersect phi of vj, so that'd be a common missing color. So we let alpha be a common missing color of I and j, and then we're going to break into three cases. So what happens when I is 0 and j is 1? So that kind of that edge E has a common missing color. What happens when I is 0? Again, I being 0 would be the center, this v naught, and some other j. And then lastly, what if I is greater than 0? So what if neither of them is the center of our fan? All right, so those will be the three cases. Here is case 1, I equals 0 and j equal 1, and I'll draw you some pictures for these. So here's again a picture. Now I've kind of gotten rid of the extra colors to clear up the picture, but we have v naught and the star v1 up to vn as the leaves, and we know that v naught and v1 then are both missing this color alpha. So I'll draw that by writing alpha and then crossing it out to denote that it's missing around v naught and v1. So E, the edge v naught v1 is not colored, but all the other ones are. What do we do? Maybe stop, pause for a moment and think what you would do in this case. Okay, now that you're back, I will show you what to do. Well, here's the easy case. We just color the edge v naught v1 with alpha, right? So we wanted to get the coloring. That's what we're assuming doesn't happen, that we can't get a coloring of the whole graph G. And so, well, here v naught and v1 are both missing alpha, so we can just go ahead and plunk alpha down, declare that the coloring, and now we've extended phi to a k-edge coloring of G, a contradiction. So that was the simple case, the kind of the best. If they just, the first two vertices are both missing a common color. So now what? Well, the next case it'll do when I is 0 and j is greater than 1. So I being the center and some non-edge. And if you think about it, that means some non-first edge, it has to be colored, right? So only that v naught v1 was uncolored, now we'd actually have a color, so let's give it a name, call it beta. So beta will be the color in phi of v naught vj. And if you think about it by definition of Vizing fan, then there has to be some earlier vertex where that color was missing. That was the definition of Vizing fan. So beta is missing at some earlier vj prime. So here's the depiction of that. We have alpha missing at v naught and vj. So there's beta, some other color on that edge, and that has to be missing at some earlier vj prime. So this is the situation. So maybe stop, again, pause, think for a moment. What would you do in this case? How can we make progress? Well, now that you're back, the key is switching again, right? So let me back up a second. Here was the picture. And now what is this path between v naught and vj, which is alpha beta? Well, this P V naught alpha beta phi path would just be the edge V naught Vj, and so I can switch on it and get some phi prime. So we go from alpha missing at V naught and Vj to now, and the edge color beta, to alpha being that color, and then both missing beta. Hence beta is missing at in phi prime at V naught and at Vj, but more importantly also at Vj prime. We didn't mess, if you stare at this picture, we didn't mess with Vj prime at all. We didn't change any edges colored around it, and so it'll still be missing beta. And now we argue that we take T prime, a new fan, to be the fan V0 up to Vj prime, and we take this coloring phi prime, and we claim that that contradicts the minimality of T and phi. So do you see why? Well, so beta is missing at V naught and Vj prime, J prime is less than J, and sure enough that is a coloring of G minus E, phi prime. But you also have to think about why it's a fan, so I'll just leave that as an exercise to you. It doesn't take much convincing, because why? Well, we didn't really change any of the colors in T prime. So whatever colors were used to verify that those edges were missing, that those colors of the edges, you know, V naught V2, V naught V3 up to V naught Vj prime, were missing at some earlier vertex. Well, none of those earlier vertices are changed in their colors. So they remain unchanged, and so they'll still have the property of being a Vizing fan. So we should spell that out in a little more detail if we were doing a formal proof, but I'll just leave that to you to do on your own time. So that's the key. So in this case too, we just have this edge and we just do the flip immediately and declare, oh, there's a contradiction with this T prime, this kind of smaller fan. All right, so we've done that. Now what else? Well, we have case 3 left, where I is greater than 0. So it's missing not at the center, but at 2 of the vertices. And if you think for a moment, those would be the only 2 vertices, I and j, where it's missing. Because if it was missing, we could restrict t down so that n is equal to j without loss of generality. And then if it was missing at 2 even smaller vertices, I and I prime, you could just assume those. So in particular, what that means is you could take a color missing at V naught, and we know such colors, every vertex has been missing some colors, and here's where we're using the fact that k is at least delta plus 1. So every vertex has some missing colors. In particular, there's one, let's just take one beta at V naught, and by the minimality of t, you can easily see then that beta is not equal to alpha. Otherwise, we would just take V naught and Vi, the fan up to there, and then that would be a smaller fan, a smaller choice of I and j. And because I reused the old pictures, let j prime equal I. So just to keep the pictures consistent, I'm just going to relabel I to j prime. So then here's kind of a picture, and there's going to be 2 subcases to this case. So case 3a will be that is the vertex V naught not in the path from Vi, which here I've relabeled to Vj prime, alpha beta phi. So what I'm going to do, I'm going to take this kind of kept chain starting at Vi, now labeled Vj prime, and what happens? So it's alpha's missing there, so then the edge, maybe it's just the single vertex, but if it's a path, then it's going to start with a beta colored edge because alpha's missing around it, and then go alpha, and so on. And the case we'll do now is, what if this path doesn't wrap around to V naught? So then we can do something pretty sneaky, we switch. So what should we do? We do the switching. So here was the old picture where alpha was missing, and then you had beta alpha as the colors, and now we have beta missing, if you think about it, and alpha beta, so on, are the colors of this path. So why is this good? Well, now look at this picture. Beta is missing at V naught and at Vi. So do you see why that's good? Well, that means we can choose this smaller fan T prime, as a bit in the last picture. So V naught up to Vi, and phi prime will end up contradicting the minimality of T and phi, because we'll be using 0 and I instead of I and j. And again, a little exercise, you'd have to argue why this is still a Vizing fan. So pause for a moment and think. For the same reasons, right? Because we don't end up adjusting any of the colors that appear. Why? Because, so this maybe takes a little bit more thought, because right, you might complain maybe we end up changing the missing color at some earlier vertex, but no earlier vertex can be missing alpha or beta because we assume the minimality. So there's a slight slippery point there of a technicality, but if you realize really, again, beta only appears, beta was only missing once, then you'll realize that indeed we can get this fan, this smaller fan. All right, so we've done that. And now what? So beta was only missing at V0, so then we get beta missing also at VI, and we get a smaller fan. So again, think through that argument on your own time. We could have written out if we're doing a formal proof. All right, so we've handled the first case, right? So the idea was, we looked at this path coming from VI. If it didn't go to V0, we can just flip, get a smaller fan. Great. The other case, obviously, then, is it goes to V0. And therefore, it actually has to end in V0, because V0 doesn't have beta. So here would be our path. I've kind of drawn it, and I mean, it doesn't have to exactly go in that direction. It could go in with some later edge after Vj or some earlier edge, but I'm going to actually draw it like it's going between J prime and J, because that's the worst. So if you think about it, it can be some earlier edge, because then it'd have to be missing at some earlier vertex, and then again, you could choose Vi in that earlier vertex as more minimal. But so this is kind of the worst picture currently happening. What do we do? So maybe pause and think for a moment, what would you do in this case? So before we were going to flip PV, J prime here, but can we do that? Well, it wouldn't really change the situation much, right? You would just be kind of flipping alpha and beta, and maybe that ends up messing a bit with the colors, so we could try that. Or alternatively, maybe more intellectually consistent is instead just look to Vj. So look at Vj and look at the path, this PVJ alpha beta phi path coming out of it. So that would start with beta, because alpha is missing at Vj, and go beta, alpha, etc. Could just be a vertex, but let's say it's longer. It doesn't go to V0 is the important part, right? So here we're going to use this nice fact that comes up in edge coloring, that a path can only have two ends. So if we already know the two ends of the earlier path, that where they were Vj prime and V0, then they can't be Vj. All right, so then we have this distinct path, this PVJ. What do? We flip it. So here was the old picture where alpha was missing and you went beta alpha. Now we flip it, so we've switched it as noted in the picture. And now beta will be missing at Vj, and it'll go alpha, beta, etc. And why is that good? Well, beta is now missing at V0 and Vj. So we've switched, instead of being Vj and Vi that are missing alpha, now it's V0 and Vj. And so now, I won't draw it here, but you can just take the fan. Let's only take it up to Vj, which we could have really assumed J was equal to N anyway by minimalities. And then you'll get a contradiction. Why? Because now we've traded J and I for J and 0, which is smaller by that second condition. We wanted to minimize that I, or here denoted J prime. So we're going to minimize that and get a contradiction. Great. So again, exercise technicality, you'd have to think about why it's a fan still when you're doing all these arguments. So maybe pause and think again for a moment. And what's the answer? Well, it's the same standards, right? Did we end up changing any edges around? No, because we didn't change any of the edges around V0, because then that would have been an edge incident with V0. It would have been in this PVJ prime. Did we change the missing colors at other vertices? Because that would be problematic if that would ruin the fanness, the Vizing fanness. But again, it would have to mean that alpha beta was missing somewhere else in the picture, which would then give you some more minimal choice for I and J, a contradiction. So those kinds of arguments you have to do to make a real formal proof. So here we're doing kind of a mix where I'm going to leave out the technicalities, because that would add a lot of writing, but just pointing out where they are verbally here, but covering the major cases. So we had kind of three major cases. In one of the cases we just colored, that was case 1. In the other case we just did a quick flip, and then that got us to a more minimum choice, more contradict the choice of T and phi. And then here the hard case where the two missing vertices were not the center, we either flipped one path if it didn't contain the v0, or we flipped the other path. Whichever one kind of doesn't have the v0, ideally the earlier one will flip that path, and then that will give us a smaller fan either in the j or in the I, a contradiction. So now we are ready to prove Vizing's theorem. We've concluded the proof of our nice lemma about the missing disjoint colors and the disjoint missing colors. So what's the proof of Vizing's? Here's the idea. Very simple. We're going to take a maximum Vizing fan, so maximum size, maximum number of vertices, and apply the lemma for contradiction. How does that go? So I'll just quickly run through this somewhat formal proof. Let G be a counterexample with V of G minimized. So again, minimum counterexample. Hence the has to be some edge. We'll call it E, because if there were no edges, there'd be nothing to show. And by the minimality of G, G minus E has a delta plus 1 edge coloring phi of G minus E. So we, again, by minimality, get this nice coloring. So that puts us in a position to use our lemma. But first we'll take a fan. So we'll let T be this Vizing fan with respect to E, V0, and phi, such that N is maximized. So as promised in the idea, I'm going to take a maximum fan from this V0, V1, and we'll go up to N there. And then what? Well, by our nice, you have disjoint missing colors lemma, you have phi of Vi intersect with phi of Vj is empty. So they're all, for all distinct I and j and 0 to n, so they all have disjoint missing colors in the Vizing fan. Okay, what use is that? Well, then let's finish off the proof quickly. It goes like this. Take all the colors that are missing naught at the center. So here I'm going to write this as the union I and n of phi Vi. Those missing colors, again, at Vi. So now what do? We go ahead and by our lemma, we know that x is at least n, right? There's at least n of these vertices, and so by our lemma, x is at least n. So we have at least n missing colors not at the center. So there exists, if you think about what that means there exists an alpha in one of these missing colors that doesn't appear at any of the edges in the fan. Why is that? Because there's only n minus 1 such edges, so there's at least n such colors, so there has to be some color that doesn't appear on any of the edges of the fan. And then, well, what do you know? Well, again, using our lemma, we know that that color can't also be missing at V0, so there have to be some edge En plus 1 where it appears. So there have to be some edge colored alpha. And we can call it En plus 1 with V0 Vn plus 1. So we kind of label that the other end of that vertex. But then you get a contradiction, right? Then T plus En plus 1 is a larger Vizing fan with respect to E, V0, and phi, contradicting the maximality, right? So we just kind of make a little counting argument and realize that if you take a maximum one, it won't actually be maximum. So it's very delightful. So that means actually if the whole thing collapses contradiction, you could have extended the coloring. So this goes by contradiction. You could actually turn this into an algorithm that tells you how to color by doing those various switches, but this ends up concluding our proof. So we can make a nice counting finish to a kind of contradiction induction proof just using our nice lemma from earlier. And here again, we used all the concepts. We used missing colors, we used count chains, we used the switching a lot, just split it up into different cases to figure out how we should make progress. So that's really what you should be thinking about. This is, we want to show this key lemma about the colors. How do you do that? You think about it by making progress, right? So we say, well, we want the missing colors to be for I and j, and you want to minimize j, and then subject to that minimize the I, and maybe we can do flips to get it to kind of be 0 and 1, where we can just end up coloring E. So that's a very nice proof of Vizing's theorem. Until next time, where we're going to go ahead and move beyond Vizing's theorem, and we'll talk about more edge coloring. So there's additional edge coloring conjectures and a lot of additional results since Vizing proved his theorem in 1964. But that concludes our proof of Vizing's theorem, and please read Diestel if you want to see a slightly different, maybe shorter proof. And there's even yet other proofs of Vizing's that I didn't cover here, more in line with original Koenig's, but all of them using count chains generally. So until next time, see you then.